Hey everybody, it's Monday, May 10th, and as you can see here in the aim today, our goal for today's video is to review the free response questions that were assigned for work on Friday, the AP FRQ review day 15 problems. All right, let's take a look. This first question was on the AP exam in 2017. It says here the left end of a rod of length D and rotational inertia I is attached to a frictionless horizontal surface by a frictionless pivot, as shown above. Point C marks the center or midpoint of the rod. The rod is initially motionless, but is free to rotate around the pivot. A student will slide a disk of mass m disk toward the rod with a velocity v0 perpendicular to the rod. The disk will stick to the rod a distance x from the pivot point. The student wants the rod disk system to end up with as much angular speed as possible. Obviously here, that's a pretty important piece of information. So part A of this question here says, suppose the rod is much more massive than the disk. To give the rod as much angular speed as possible, should the student make the disk hit the rod to the left of point C, at point C, or to the right of point C? And then you have your options, and it says briefly explain without manipulating equations. Now, there are a couple of ways that you can go about answering this question here, but regardless of the analysis that you use, the basic idea is, and both analyses lead you to the exact same conclusion, that the farther away the disk is, the faster the rod will end up going here. So the answer is to the right of C. Now, there are two ways that you can go about doing this. The first way is by using basically the torque equation to come up with an idea about torque. And the second way is by talking about the angular momentum of the disk, which, notice, because it is a point mass, meaning it is not itself rotating, but rather is moving tangent to the circular path that is going to end up being experienced by this rod, it has an angular momentum given by the equation mRV. So, like I mentioned, there are two ways that you could look at this. Remember, when we were talking about just like regular old collisions, we said you can look at it from the standpoint of conservation of momentum, or you could look at it from the standpoint of like Newton's third law. They exert equal and opposite forces on each other. They exert those equal and opposite forces for equal amounts of time. And as such, the impulses are equal and opposite. It's the same idea here. You can say first that when the disk crashes into the rod, it is going to exert a force on the rod. And because that force is perpendicular to the moment arm here, or that position vector, remember, drawn from the pivot point to the point of application of the force, it's going to exert a torque. And according to the torque equation, torque is maximized when the distance is maximized. Now, the other way that you could look at it is, well, the disk here is going to stick to the rod. And so that means it's going to impart its angular momentum. Whatever angular momentum it has, it's going to impart that angular momentum to the rod. And according to the equation for the angular momentum of a point mass, that angular momentum is directly proportional to the distance from the pivot point. And so notice both of these analyses suggest you want to make it be as far as possible from the pivot point, which means here to the right of C. This is what I wrote. The disk must hit the rod to the right of C. In order for the disk to, quote, give the rod as much angular speed as possible, it must change the angular momentum of the rod as much as possible. Since torque is equal to the time rate of change of angular momentum, remember, that's a super important equation in the reference table. It's not solved for torque, it's solved for delta L, but it says delta L is torque times time. The fact that the disk must change the angular momentum as much as possible means it must exert as large a torque as possible on the rod. When the force exerted by the disk is farther from the pivot point, it exerts a larger torque on the rod because the torque is directly proportional to the distance from the pivot point. Then notice here I sort of snuck in the angular momentum explanation. Note this makes sense because the puck itself will have more angular momentum when it's farther away, given by the equation mRV, so it can impart more angular momentum to the rod. Take a second to pause this video here. Make sure you have this written down. Check this against your explanation and any parts that are missing from your own. And when you hit play, we'll take a look at the scoring guide. All right, let's take a look at the scoring guide here. Notice I certainly over-explained a little bit. This part was only worth 1 point, but the correct answer here was to the right of C, and the reasoning cannot earn credit if you picked any other answer. And they basically gave you a point here for explaining that the torque exerted by the disk or the angular momentum of the disk is greater when you are farther from the pivot point. Example 1 says the disk exerts a greater torque on the rod when it pushes farther from the pivot point. Example 2 says the disk has a greater angular momentum when it's farther from the pivot point. the disk loses almost all of its speed during the collision and hence gives the rod almost all its angular momentum. So the rod ends up with more angular momentum when the disk hits farther from the pivot. Cool. Take a second to pause this video here, making sure you understand all aspects of that scoring guide. And when you hit play, we'll move on. All right, moving on to part B here. Part B says, on the internet, a student finds the following equation for the post-collision angular speed omega of the rod in this situation. And it says omega equals m disk x v naught over I. Regardless of whether this equation for angular speed is correct, does it agree with your qualitative reasoning in part A? In other words, does this equation for omega have the expected dependence as reasoned in part A? Now, I thought that last part was kind of generous, because what you need to start to realize as we approach the test here is that when they ask you, does this agree with your reasoning, basically what you want to talk about is proportionality. They end up essentially telling you, in other words, look at the proportionality and see if it makes sense based on what you said. And according to that equation, there are a couple of things we can say. We can say the angular velocity is directly proportional to the mass. We can say it's directly proportional to the distance from the pivot point. We can say it's directly proportional to the linear velocity. We can say it's inversely proportional to the rotational inertia. Now, of course, what we talked about in part A was the distance. And so notice this equation says, as the distance increases, the angular velocity of the rod is going to increase. And that's exactly what we said. And so here, for our explanation, I just wrote, yes, this agrees with our reasoning from part A. In part A, we said the angular speed of the rod gets larger when the distance from the pivot point gets larger, which would mean that the angular speed of the rod is directly proportional to the distance from the pivot point, which is labeled x. In the equation, since x is in the numerator, the equation shows the distance from the pivot point is directly proportional to the angular speed, which is in accordance with our reasoning from part A. Take a second to pause this video here, check out this explanation, add any parts of this that are missing from your own, and when you hit play, we'll take a look at the scoring guide. All right, let's take a look at the scoring guide here. There were 2 points for this one. Correct answer is yes. If no is selected, you could still earn credit if you're in, if you got the answer wrong in part A. Basically, they wanted it to be consistent with whatever your answer was from part A. So notice the first point is for a selection consistent with the selection from part A, and then 1 point for indicating that the equation shows that omega increases with an increasing x. So if you said to the left of point C earlier, and then you said no, because this shows that omega increases with increasing x, you can earn the points here. And I think that's an important idea, that you want to just answer these things and be consistent with your answer, because if you answered this totally wrong, yeah, you'd lose the first point in part A, but you would have gotten full credit for this. You would have said, no, I said it's got to be closer to the pivot point. This equation says omega is directly proportional to x. That shows the opposite. This equation is wrong. Now, that's dead wrong, but ultimately you could still earn credit, and that's pretty cool because that is the application of a physics skill. Take a second to pause this video here, make sure you understand all aspects of the scoring guide, and when you hit play, we'll move on. Moving on to part C here, it says another student deriving an equation for the post-collision angular speed omega of the rod makes a mistake and comes up with omega equals I x v naught over m disk d to the fourth power. Without deriving the correct equation, how can you tell that this equation is not plausible? In other words, that it does not make physical sense. Briefly explain your reasoning. Now, if you remember, this was asked after the unitless constant controversy, and I don't want anybody to, focus in on that too much here, because I think it's important to realize that the units are not going to be the reason why this equation ends up being incorrect. The units for I are kilogram meter squared, then we have meters for the x, then we have meters per second, then we have the mass of the disk is kilograms, and then d to the fourth is meters to the fourth. And so notice here, kilograms cancel kilograms, meter to the fourth cancels 1, 2, 3, 4 meters, and the unit for this thing ends up being 1 over seconds. And since we treat the radian as a 1, it does have units of radians per second. Forget about the units. It's all about the relationships. This equation shows omega is directly proportional to I, directly proportional to x, directly proportional to v naught, and then it shows it's inversely proportional to the mass of the disk and inversely proportional to the length of the rod to the fourth power, because the length of the rod was labeled as d. Now, these relationships don't matter. These are the relationships you want to focus on. Now, of course, the reason why that's true is because they're wrong. This says the angular velocity gets bigger. The angular velocity of the rod gets bigger when the rod's rotational inertia is bigger. There's no way that could possibly be true. This equation also says when the disk has more mass, the angular velocity gets smaller. But as we said, when the disk has more mass, the angular momentum of the disk gets larger. That means it should exert a larger torque on the rod. My explanation here looks like this. I did it in two parts. This equation has the wrong mass relationship and the wrong rotational inertia relationship. Now, I think the rotational inertia relationship is the most obvious. If I had to bet my life on it, I would guess that most of you wrote about that. I was talking about the angular momentum a lot here in the beginning, and so I figured I'd stick with that. And I wrote here, the equation the student derived shows that the angular speed of the rod is inversely proportional to the mass of the disk, which means that the larger the mass of the disk, the smaller the angular speed of the rod. This is wrong because if the disk has a larger mass, it'll have a larger angular momentum, which means it will impart more angular momentum to the rod. I think the second explanation is way easier and straightforward. I wrote here also, this equation shows the rotational inertia of the rod is directly proportional to the angular speed of the rod. A larger rotational inertia means that the rod will be harder to rotate, which means it should have a smaller angular speed, so that's definitely also wrong. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to the scoring guide here. You got 1 point for focusing on functional dependence instead of, for example, considering the units. Again, they really tried to push everybody away from looking at the units. Watch, the freaking units will be on there on this year's test. I would say take 2 seconds to check on the units, but you really want to focus on, as they say here, functional dependence, or as I would say, you want to focus on proportionality. You get 1 point for addressing the mass of the disk, the rotational inertia, or both, and you get 1 point for correctly concluding that the equation is wrong because of the proportionality that's shown for M or I, or both. And their example here says if M disk is large, then more angular momentum will be transferred during the collision, but if the equation shows the angular speed, decreasing with angular M disk because it is in the denominator, obviously, you could just reverse that for the I explanation and it would get you full credit as well. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on to part D here. Part D says for parts D and E, do not assume the rod is much more massive than the disk. Immediately before colliding with the rod, the disk's rotational inertia about the pivot is m disk x squared, and its angular momentum with respect to the pivot point is m disk v naught x. Derive an equation for the post-collision angular speed omega of the rod. And it says here, express your answers in terms of m. Geez, that's the wrong first variable. In terms of d, m disk, I, x, v naught, and physical constants as appropriate. So, like I said, there are a lot of ways that you can go about answering this problem. You can talk about torque, you can talk about whatever, but I think the most appropriate way to go about doing this is conservation of angular momentum. Now, it's important to take a moment to think about some of the things they said. Notice here, they say immediately before colliding with a rod, the disk's rotational inertia about the pivot is m disk x squared. That makes sense. Remember, we said for a point mass, the rotational inertia equation is given by mr squared. There is no fraction in front or anything because it's just one little point mass, not actually itself physically rotating, but just set some distance r away from the pivot point. So in the beginning, we just have the angular momentum of the disk by itself. Now, how do we know that the only thing contributing angular momentum to the system is the disk by itself? Well, the rod's not rotating. It only begins to rotate once it collides with the disk. So at the end, we have the disk and the rod, but they're together. It sticks. And so the basic idea here is it's basically like a perfectly inelastic collision where you have two separate objects, they collide, they stick, bada boom, bada bing. So let's start here with the physics principle. We'll say here the initial angular momentum is equal to the final angular momentum. I'm actually going to write here L disk is equal to L disk plus rod, just so we don't forget that that's the case going forward. Now, whenever we've done these conservation of angular momentum problems, we've never done that, but just for now, I'm gonna. So they actually already told us here the angular momentum of the disk with respect to its pivot point is m disk v naught x. Whoops. So I'm going to write here m disk v naught x. And the angular momentum of the disk and the rod, it's important to realize, is going to be the rotational inertia of the disk plus the rotational inertia of the rod times omega final. And so notice here, to solve this for omega final, all I have to do is divide by the sum of their rotational inertia. So I have the mass of the disk, v naught, x, and then over the sum of their rotational inertias, disk plus rod. Now, the only thing I really need to do to finish this thing up, because notice they told me to express the answer in terms of I, which was the the rotational inertia of the rod, is I just need to sub in the rotational inertia of the disk. And so here, I'm going to write m disk v naught x over m disk x squared plus I r. And that's it. Notice, because the mass of the disk is in the numerator multiplied, but in the denominator multiplied by x squared and then being added to something else, you can't really make a nice, clean cancellation here. And so that's pretty much it. Take a second to pause this video here and write that down, adding any parts of this derivation that may be missing from your own. And when you hit play, we'll move on. All right, let's take a look at the scoring guide here. Notice they gave you 1 point for using an expression of conservation of angular momentum for the disk and rod. So if you just try an angular momentum conservation, you got a point. It says, notice, though here this point is not awarded for equating angular and linear momentum. Obviously, that's not how it works. L naught does not equal like P final or whatever. It's L equals L. You get 1 point for indicating that the angular momentum of the initial system is m v naught x, which they told you. You get 1 point for a dimensionally correct expression for the post-collision angular momentum that includes I omega. And you get 1 point for indicating the correct rotational inertia of the system after the collision is I plus m disk x squared, because the disk is treated as a point mass. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the last part. All right, moving on to the final part of this question here. It says, consider the collision for which your equation in part D was derived, except now suppose the disk bounces backward off the rod instead of sticking to the rod. Is the post-collision angular speed of the rod when the disk bounces off it greater than, less than, or equal to the post-collision angular speed of the rod when the disk sticks to it? This is not the first time we've seen a question like this. I really hope you guys nailed this, because we talked about this a hell of a lot when it came to conservation of momentum. We talked about it again when we got to conservation of angular momentum. I gave you a free response question with the pumpkins, remember, where there was like the embedded arrow, the pass-through arrow, and the bounce arrow. When something bounces, we get greater impulses. The rebound and the reverse in direction is the whole deal for this kind of problem. Keep in mind here, let's just say, now I'm looking at this sideways. That's kind of annoying, I guess. But let's just say here that this is the pivot point. When this disk comes in, it has an angular momentum equal to mrv naught. If it bounces off here now with some angular momentum, let's just say it came back with the same speed, and it was mrv naught, but it's negative now because it's going in the opposite direction. The basic idea is the change in the angular momentum would be final, negative mrv naught, minus initial, mrv naught. So we would have a change in angular momentum of negative 2 mrv naught. The idea is when something rebounds and reverses direction, you get a bigger impulse, or in this case, angular impulse. And if its change in angular momentum is bigger, in order to conserve angular momentum, that means the change in the angular momentum of the rod must be bigger. Because at the end of the day, the total angular momentum between these two things has to be equal to mrv naught, and it's got to be positive. So that means for the disk, its angular momentum would have to be some number equal to 3 mrv naught, so that when you add these two things together, it adds up to 1 mrv naught. Here's what I wrote. Greater than. the angular impulse is experienced by each object will be the same. This means that the change in angular momentum experienced by the disk will be equal to the change in angular momentum of the rod. When the disk rebounds, it ends up having angular momentum in the opposite direction. In the case of the actual diagram, that'd be clockwise, which means the rod must gain more angular momentum than was originally possessed by the disk in the counterclockwise direction in order for the final angular momentum to be equal to the original angular momentum. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to the scoring guide here. Notice they gave you a 1 point for indicating, the correct answer is greater than. They gave you 1 point for indicating either directly or by analogy to the linear case that the disk's angular momentum with respect to the pivot point changes more in the bouncy scenario than in the original scenario, or for using a similar argument in terms of impulse. Notice it says here, note, this point is for describing what happens to the disk. And then notice here, it says, note, the second point is for what's happening to the rod. You get 1 point for using conservation of angular momentum or momentum impulse reasoning to conclude that the rod gains more angular momentum and hence more angular speed in the bouncy scenario. Their example response says, after the bouncy collision, the disk has angular momentum in the clockwise direction. To keep the system angular momentum constant, the magnitude of the rod's counterclockwise angular momentum must be greater than before. An important thing to realize. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the second problem. All right, moving on to the second problem here. This question was a shorter question, only worth 7 points, also on the 2017 AP Physics 1 test. It says here, a physics class is asked to design a low-friction slide that will launch a block horizontally from the top of a LAD table. Teams 1 and 2 assemble the slides shown above and use identical blocks 1 and 2, respectively. Both slides start at the same height d above the tabletop. However, Team 2's table is lower than Team 1's table. It says here, to compensate for the lower table, Team 2 constructs the right end of the slide to rise above the tabletop so that the block leaves the slide at the same height h above the floor as Table 1. So you see here how the tables are lower. So what they did was they just made this rise up a little bit. Okay. Now, part A of the question says both blocks are released from rest at the top of their respective slides. Do block 1 and block 2 land the same distance from their respective tables? Justify your answer. So when they say land the same distance, we're talking about a projectile motion problem. Now, I hope we've done enough of these already for everybody to realize how you're supposed to answer a projectile motion range question. The range of a projectile is given by the equation v naught x times t. And you better believe, because those are the two things in the equation, those are going to be two things they're going to give you points for mentioning in the scoring guide. The answer here, it says, do block 1 and block 2 land at the same distance from their respective tables? The answer here is no. And they're going to want you to explain about the time and the horizontal velocity. Now notice, they say here they're the same launch height because this group built their little ramp up at the end. The time for an object to reach the floor when it's launched horizontally is given by the equation square root of 2 delta y over ay. Same height, same acceleration, same time. So the big question here is, what is ultimately going to make this range different? And it's this gap in the heights. Block 2 is dropped from a lower height because the table is lower. That means it's not going to gain as much speed. What I wrote here is no, the blocks do not have the same range. The range of the blocks is determined by the product of their horizontal launch speed and time of flight. Since the edges of their respective tables are the same height above the ground, the time of flight of both blocks will be the same. This means that the differences in their range are determined by the differences in their horizontal launch speed. Since the height of block 1 above the edge of the table is higher, the block will have a larger initial gravitational potential energy. That, of course, is true with respect to the edge of the table. Also, though, with respect to the floor. I wrote then, this means that when the gravitational potential energy is converted to kinetic energy, the final kinetic energy, and thus the final speed, will be larger for block 1. Since the range is directly proportional to the launch velocity, the fact that block 1 has a larger launch velocity means it will reach a larger range. They want you to talk about the time. They want you to talk about the speed. Take a second to pause this video here and write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll move on. All right, moving on to the scoring guide here. Notice this was a 3-point question. The correct answer here is no. And it says if the wrong answer is selected, partial credit can be earned for the justification. You got 1 point for attempting to use conservation of energy to compare the two blocks. You got 1 point for explicitly indicating that the launch velocities are different, v naught x. And then you get 1 point for stating or implying that the time to reach the ground is the same for both blocks. So notice here, there's a v naught x point, there's a time point, and hey, it's a ramp and not a straight line ramp, so it's definitely not going to be an inclined plane problem. It's a ramp, so you use conservation of energy. That's pretty easy to see in terms of like predicting what they're going to put in the scoring guide. The example says the amount of potential energy converted to kinetic energy is different for the two blocks. The potential energy is proportional to the change in height, which is smaller for block 2. Therefore, at the edge of the table, block 1 will have more kinetic energy than block 2, and hence a larger speed. The launches are both horizontal and from the same height, so the blocks will spend the same amount of time in air. Because d equals vt, the distances will be different for the two blocks as their speeds are different. Take a second to pause this video here and make sure you understand all aspects of the scoring guide. And when you hit play, we'll move on. All right, moving on. It says here for part B, in another experiment, teams 1 and 2 used tables and low friction slides with the same height. Remember, this is one of the general notes in like the AP physics exam review concepts. Low friction means no friction. However, the two slides have different shapes, as shown below. Both blocks are released from rest at the top of their respective slides at the same time. And it says which block, if either, lands farther from its respective table. Now, notice here, the tables are the same heights. So the times are going to be the same. And the height of the block above the bottom is the same. So they're going to have the same v naught x. And if they have the same v naught x and they have the same time, then they're going to have the same range. The answer here is the two blocks land the same distance from their respective tables. I wrote here the two blocks land the same distance from their respective tables. The range of the blocks is determined by the product of their horizontal launch speed and the time of flight. Since the edge of their respective tables are the same height above the ground, the time of flight of both blocks will be the same. Since the height of both blocks above the edge of the table are the same, both blocks will have the same initial gravitational potential energy, once again, with respect to the edge of the table, but also with respect to the ground. This means that when the gravitational potential energy is converted to kinetic energy, the final kinetic energy, and thus the final speed, will be the same. Since the range is directly proportional to the launch velocity, and the time also, but that's not really the point here. What's different from the first situation is that the launch velocities are different. Since the range is directly proportional to the launch velocity, the fact that the blocks have the same launch velocity means they will have the same range. Take a second to pause this video here, write that down, adding any parts of this that may be missing from your own explanation. And when you hit play, we'll take a look at the scoring guide. Now notice here, this one was pretty straightforward if you got the first part. Correct answer listed there, same distance from their respective tables. You got 1 point for talking about energy, and then you got 1 point for talking about the launch velocities being the same. I mentioned the time just because it doesn't hurt. Obviously here, though, they did not give any credit for that. They only gave credit for talking about the launch velocity and energy conservation. They basically tested your ability to determine the times were the same in the previous problem. Take a second to pause this video here and write that down, making sure you understand all aspects of the scoring guide. And when you hit play, we'll move on to the last part. All right, moving on to the last part here. Part B2 says, now we've got the same setup. Both blocks are released from the top of their respective slides at the same time. Which block, if either, hits the floor first? Now, if you had trouble with this, I made a video about this. It was called High Road, Low Road. Look for it. We discussed one of these kind of questions in that video. Block 1's going to hit the floor first. The basic idea is this slide is, in the context of that video, a low road. Let's just look at it like some arbitrary distance over, like let's say here. Notice if we go, let's just assume those are the same. If we go some distance over to just look at what the block is going to be doing in a few seconds, block 1 is way lower than block 2. Look at that difference. Because block 1 is way lower than block 2, it's going to end up gaining more speed quicker. And because it's gaining its speed quicker, it's going to end up moving down the ramp much quicker. And because of that, it's going to end up hitting the ground first. I wrote here, block 1 reaches the ground in less time. Since the ramp for block 1 is curved in such a way that the block can, quote, lose more height quicker, the object loses gravitational potential energy faster, which means it will reach its maximum speed in less time. As a result, the average speed of block 1 will be larger. Since the average speed is inversely proportional to the time spent traveling down the ramp will be smaller, which means it will be launched off the side of the table in less time. Since the blocks will be in air for the same time, the fact that block 1 is launched in less time means it'll hit the ground first. I think it's really important to remember that when you are trying to explain why something covers a certain distance in a certain amount of time, that the average speed or average velocity, obviously depending on the context, but the equation v equals d over t in whatever form you use it is going to be really crucial. The reason why, especially if they have the same distance, is because then you could say if the distance is fixed, the time is inversely proportional to the average velocity. Now, when an object is accelerating, the average velocity generally, this of course is only true if the acceleration is constant, but you can at least conceptualize the average velocity equation as being equal to the arithmetic average of the initial and final velocities. So the basic idea is, because the time is going to be inversely proportional to the average velocity, it's a quick and easy way to explain why two things maybe will travel the same distance in a different amount of time. Take a second to pause this video here, write that down. When you hit play, take a look at the scoring guide. Looking at the scoring guide here, obviously correct answer, block 1. 1 point for indicating that the average speed or velocity on the slide is higher for team 1, or that block 1 reaches its maximum speed in less time. And then for a valid explanation of why the average speed or average velocity is higher for team 1, or why block 1 reaches its maximum speed in less time. Their example was pretty quick, I thought. It just says because the ramp on table 1 is initially steeper, block 1 has a higher average speed while it's on the ramp, so it launches off the table before block 2. Pretty quick, pretty easy, pretty straightforward, but that's the idea. Take a second to pause this video here and write that down. And when you hit play, we'll wrap it up. All right, everybody, that is it for today. I hope you are starting to realize some of these big picture forms for the test. I don't mean concepts, because these were two totally different kinds of problems. One was a basically conservation of energy and kinematics problem, while the other was a angular momentum problem. But I think the point about the way you answer the questions was the same. It's all about using the equations to come up with answers and justify responses. That's the key. And I want you to keep that in mind going forward. Couple weeks, 2 weeks from today, you'll be taking the test. Can you believe it? Remember, this work over the next 2 weeks is really going to make all the difference. So keep at it, everybody. All right, guys, have a good one.